Welcome back, class. So in this video, I'm going to talk about ways that we can monitor or follow a titration. So one classic way to do it, right, is simply to measure the pH, right? So we could measure the pH with a pH probe, right, which is a device that measures the conductivity of the solution that's honed in to look at hydronium ion. And so we can measure that hydronium ion using this pH probe as we progress through the titration. And of course, that can then be converted into a pH, and we can plot the pH based on that reading, that signal from the pH probe. So a pH probe is one way. Now, if you don't have access to a pH probe, or sometimes we just use it as a secondary indication, you can use, again, what's called an indicator. And this is going to be a material that changes color during the rapid rise that we find in our pH curve, right? So changes color somewhere near the equivalence point. Now, if we look at these titration curves, the big thing that always pops out, right, is we have a very large change in pH over very small additions of what we're adding from our burette, our titrant, near the equivalence point. So this gives us sort of a little bit of leeway, right? The color change doesn't have to occur exactly at the pH of our equivalence point. If it occurs anywhere sort of within that pH range where we're having that rapid rise, then the volume is going to be fairly close, right, to what, we're looking for as the volume at our equivalence point or the end point. So just to make a distinction between those two terms, right, the equivalence point is the stoichiometric point, right? So that's the point that's based on the moles of acid equal to moles of base. So that's when the reaction is complete. Right? So the equivalence point refers to the reaction itself, so the chemical process going on. The end point is the color change, right? So the end point is specifically talking about the indicator and its color change. So the end point is the color change of the indicator. The equivalence point is when the neutralization is complete, right? When the moles of acid equal to moles of base. And the idea is we can get those two things to overlap. Then the end point of the indicator can tell us the equivalence point of the titration or the reaction. So the way we can do that, right, again, is if that color change occurs within the same range as what we see that rapid change where the equivalence point's at. Now, one guideline that could be used is if we look at the pKa of the indicator, right? So these indicators are typically acids and bases, right? And the idea is they're moving from the acid form to the base form during the titration, and they happen to be different colors in solution. And so we see that color change when the indicator changes from an acidic form to a basic form. But if we pick one where the pKa of our indicator is close, right, to the pH at the equivalence point. Now, we'll see when we look at a table of them that we got a pretty good range. So phenolphthalein, one of the most common pH indicators. And so it changes from clear in acidic solutions to a pink, light pink at the equivalence point, which is what we're looking for. And then eventually, when you keep adding it, it gets more to this magenta color when you get past the indicator. And so you can sort of look at this test tubes here, and you can see that, as we're going through the early part of our titration, right, where the pH, as we've seen, is going to range between 2 and, say, 5, right, we're going to be colorless. Now, for phenolphthalein, you can see that color change really occurs between 7 and 9, right? And so we're really pinpointing somewhere around that 9-ish, that we're going to see that visible color change. And that's good for us because the typical pH at the indicator of these titrations, whether they be strong acid, strong base, or weak acid, strong base, right, is going to be in that range between 7 and 9, right? So you can see the chemical reaction, right? We have the acidic version, right, where we can see these, OH groups here. And this is colorless as we undergo the reaction. Right? And we form the basic version. We get a pink color here. And of course, the formation of hydronium ions. Right, so this is our colorless version, right? And so this is the form that's stable under acidic conditions, and under basic conditions we have this form plus small amounts of hydronium ion that form. Now, again, this hydronium ion isn't going to have really any effect on the pH because you have such a small amount of these indicators in there, right? Now, this is just another example of an indicator. This is methyl red, and you can see it has this color change where it's magenta at low pHs, and you see this shifting into an orange to a yellow. Again, this one has a little bit earlier shift, right, between 5 and 7, right? So this might be appropriate for, a different kind of titration where your equivalence point is going to be, acidic versus basic. Okay, so I've already talked about these, but I just put these in for a little bit of, extra emphasis that we're monitoring at the equivalence point, and we want to match up the end point or the color change of our indicator with the equivalence point of our titration. So just for fun and reference, we can look at a table of all kinds of different indicators, and you can see that I'll highlight phenolphthalein here. And so you can, if you look at the color change is occurring right there, it starts a little bit above 8 and fully changes color in that, 8 to 9 region as that shift. Right? But of course, again, we have, our color change, right? If we think about the equivalence point, right? The equivalence point really starts somewhere out in here, right? And goes to somewhere in here, right? So as long as this color change occurs within that range, right, we're going to be able to get a reasonable volume matchup. Our equivalence point is going to be able to overlap with our end point, which is what we want, right? And we rely on the fact that we have a very small volume shift within that large pH range. And of course, if we look at that, there's a bunch of other indicators that we could use. So, methyl red that I mentioned, right? We could also use it for this kind of titration. Now, it may be better suited to something where we're doing, a weak base, strong acid kind of titration, or a different kind where the equivalence point is going to be closer to this in the acidic range. But it could be functional even for this kind of titration. And so there's a wide range to choose from, and we want to choose one. Again, the key is to match up the color change, the end point, with our equivalence point. All right, so in the next set of videos, going to be looking at this concept of buffers.